Tonight we talk about capillary pressure, and since this is my video, I'll mention that today's date is the 6th of September, 2017. Did anything important happen today? No? Cam, what is the date in terms of the Trump dynasty? Day number 158 or something like that? You're not counting? Anybody else? Eric, you counting? I'm sure you are. Eric's got Fox News imprinted on his forehead, so I'm sure. Gabe? No habla English? Okay. Anybody else? Anything important happen on the 6th of February? A week from today is my sister's birthday. And I don't know if I told you, but I'm going to wait an extra week to call her, just so we'll have something to talk about. You know, she'll say, "Why didn't you call me on my birthday?" And I'll say, "I forgot." And then she'll scream. And then in about another minute, we'll close the call, and I'll be happy for a year. So there we go. Tonight we're going to derive the equation for a single capillary. And this equation has a relatively easy derivation, but it's an important one. Now, obviously, everyone in here has given blood at some point in their life, I hope. Have you guys ever given blood? No? Never? You wouldn't give blood? You'd give blood to save my life? Probably not, right? Okay. Have you guys ever had them take a capillary and put it on your finger and it draws the blood up into it? Okay. What's the force happening there? Is it suction? No. What is it? It's an attractive force. Where's my chemies? Here and here. Sorry? It's adhesion tension, right? And the blood pulls itself into the tube as far as it can. What is the definition of as far as it can? The weight, right? The height is proportional to the weight of the fluid that the adhesion tension can pull up. So the smaller the diameter, the higher it will go. In theory, if you had essentially a zero diameter, it would go to infinity. Okay? Have you guys ever thought about that? If you got pulled into a black hole, they say it stretches you into single molecules. Or atoms. Sorry, not molecules. You guys don't think about things like that? Yeah? Mr. Mayo tonight he'll sit awake and think about being pulled into a single atom through a black hole. And the way we're going to drive this is with a simple force balance. It'll be straightforward, and we'll be done. That's one tube. Now, last night we talked about how to take a bundle of tubes and calculate an equivalent permeability. Tonight we're going to do something similar to that. We're going to take a bundle of tubes and calculate a permeability, but it'll be using this concept of capillary rise. The details of this derivation are not in the notes. They're in the Nacorn, Thapp, and Evans paper. And if you want to go back to the original, it's the Berdeen and Purcell papers back from the 1940s. Why were people trying to use capillary pressure as a proxy for permeability? Mr. Aldana, since you were the last one in. No comprende? All right, we'll talk about it. Anybody else want to take a shot? Ricardo? So you're a mechanical engineer? Physics, okay, very good. That means you have no practical experience, right? All right. Why would we use a measurement of pressure, an equilibrium pressure, in a particular medium to represent permeability? Right. Okay. Okay. So would you use, which is your favorite pore throat? Not the bigger, the big ist, okay? Because that represents the entry pressure. So the big ist pore throat represents the lowest pressure, the lowest capillary pressure. Is that going to correlate well with permeability? 3 options: yes, no, or maybe. It's probably more like yes, or yes minus, or maybe plus, but okay. What about the shape of the curve? Is that going to correlate with permeability? Maybe. Okay. What about the asymptote, where it goes to infinite pressure but finite saturation? No idea? So the minimum saturation would not be correlated with permeability? We already saw that it was. Sorry? You got to turn your volume up. Correct. The permeability will. Okay, so we have 3, and I realize we're talking about something you've never seen before, but we're going to have an XY plot, and we're going to have a curve on it. And that curve is going to have an intercept on the y-axis, and it's going to have an asymptote as well. And what I'm getting them to see is that, does the intercept have some physical meaning? Does the shape of the curve have some physical meaning? And does the asymptote have some physical meaning? And this is a conversation that should be had about 60 years ago, right? More or less. This would have been the conversation we had. And why would you want a proxy for permeability based on capillary pressure? Eric? You look like that little decal on the back of trucks.
Capillary pressure is something that
Easily measure. How do we measure permeability? We have to have a flow experiment. Okay, now here's the trick. How can something that represents flow be correlated to something that represents the largest pore? Okay, permeability is something that represents flow through the whole rock. The largest pore represents the minimum pressure for entry. How are those correlated? You just want them to be correlated? And I realize I'm about to make a politically incorrect statement, okay? But you want an arranged marriage between these two? Is that what you're telling me? You want permeability, which is a flow property, and entry pressure, which is just a capillary property, to somehow get married. But it's not going to be that easy, is it?
well, it won't work if the largest pore is not accessible. Is that what we're getting at?
You know, you have a deviant mind. I hadn't thought about that. But let's say it is a nice piece of rock where everything communicates with everything else. And we're going to talk about this, ladies. Just be patient. Next, as I mentioned, is the derivation of permeability using the capillary pressure curve. And this integral has something to do with what? We have a bundle of tubes, and we need to integrate the saturation profile across the bundle of tubes. That's where the integral comes from. Okay. Where does the square come from? Stare at that for a second. Ricardo? Stop calling on you, right? Miss Jen, where does the square come from? China? No, where does the square in the equation come from? That was pretty good. Where does this square come from? Mr. Ravi Kumar, you're going to get to sit in the back of the room and not have any more fun. I know how your brain works. How old are you? Yeah, but I mean, emotionally, you're like 12, right? Yeah, I quoted myself as being 12 today as well. Where does the square come from, class? Exactly. So somehow this gets squared, and when that gets squared, the radii get squared, right? And when that gets squared, this gets squared. But is it really 2? There are some people that say it's 2 plus alpha, or 2 plus beta, or 2 plus x. Some people add another parameter there. Some people say it's not even 2, it's alpha by itself. Okay. Good question. You tell me. Think carefully before you answer. It would have something to do with the pore throat distribution. And this is how people wave their hands. All the way back to Wiley, back in 1953, I think. And his paper is also included in here. They waved their hands on that. And they said it was related to, he said tortuosity, but other people said some sort of pore geometric factor or something. Whatever it is, it's a fudge factor. Okay. It's not something we're going to be able to define. In simple terms, we take the Purcell-Berdeen equation, and then we take the derivation provided by Naquinthap and Evans, and here's our equation. Ken, where is Naquinthap from? Sorry? I can't hear you.
That's not what we did yesterday?
No. Can, not Cam. What kind of last name is that? It's from Thailand, yes. Okay. And then when we put this equation in field units, this is our answer. Okay. Now, when we insert the Brooks-Corey capillary pressure relationship into that previous result, and we perform some integration, it's just a power law relationship, we get the standard equations as shown here. This is a definition of permeability based on what? Well, there's porosity, and that star means that it's 1 minus porosity, but that's okay. Beta is some fudge factor, N is some fudge factor. This is the interfacial tension. This is the displacement pressure. This is the shape of the curve, or a parameter that represents the shape of the curve, okay? So we have something we can measure here. We have something that God only knows what it is there. Something we can measure here. Something we can measure here. And something we can measure here. And we'll show you later how we're going to use this. The Brooks-Corey capillary pressure equation is given by this. And I know you're going, okay, Tom, now everything in the universe is power law. Not exactly, but the Brooks-Corey capillary pressure relationship, being power law, allows us a lot of mathematical flexibility and simplicity, by the way. Okay. And then this definition of dimensionless saturation, you can see it's given here. SW star is a traditional definition. SWD is a definition that I came up with. Now we're also at the end of this section today, we're going to talk about a type curve. Mr. Bake, Mr. Ravi Kumar, your chemical engineers, did you guys ever do type curves in chemical engineering?
I did.
Did not. No.
It's related to
Sorry?
column type curve.
Okay. But a type curve could be, for example, the Moody friction factor diagram. For example, it's dimensionless x and y axis, and then another dimensionless function. Okay? Any equation that you can write can be made dimensionless, we think, sort of, hope, whatever. And by doing that, we can write an expression on a dimensionless plot, and then we can have a dimensional plot. If they're plotted on the same scale, the same logarithmic scale, not the same numbers, but the same shape of that axis, you can overlay them and match. Why is this important? Because you can determine the parameters of the equation using this simplified graphical method. And before computers, this was really powerful. After computers, this is even more powerful. Why? Because it teaches your brain to look at the shape of the curve. Your brain is better than any computer that has been invented. I started to say that ever will be invented, but I need to probably step back from that because we may outdo ourselves one day. Your brain makes an image of something. You learn what that image is. You inherently determine what different parameters influence that. And I'll show you that when we do the type curve. This work was never published. You know, why not? Doesn't the world need another mousetrap? Not really. Anyway, this makes, good reading. Makes for people wanting to come to my class, that sort of thing, maybe. Okay, very quickly, let's talk about a few things. Math ladies, this is where we kind of get the physical part of the problem, and then we'll go back and do the derivations. So, can we have a 1-minute break? Okay. I'll go away. What am I going to go get? No idea. Do you want me to come back? Thanks for moving. What is this, ladies? Okay. Bernie, you like? Okay, distance learning land people, you can't see this, but I'm taking a capillary tube and I'm putting it into my bottle of not water. Okay. I'm blind. Oh, there, I can see it now. Okay, ladies, I don't have a very long leash. Can you tell people where it is? Uh-oh, now it's because I was shaking it, it's split apart. Let me see if I can fix that. It's really hard to blow against this. Why? Ricardo? It's a really small diameter. And just a little bit of liquid can make it crazy. You want me to show you a trick? I can fix that. Okay, so we'll do it again. All right. Ready? You want to do it? You don't have to play with it. It just does it instantly. Okay. Wipe it off on the outside. And where is it? It's about right there. Oh, no, it's all the way up here.
Oh, yeah.
Yeah. So it went up about 5 inches. Or was that 12.5 centimeters? Wait, be careful. Don't carry it from the bottom. Okay. Anybody else want to try it? No? Mr. Ravi Kumar? Yeah? Come to me. It's glass. Not with my bottle, you don't. Anybody else? Here, give one to Ricardo behind you, because he's a physicist. Ladies, you want this one? So that's the experiment that we're going to derive the equation for. And like I said, in theory, if the radius was small enough, it would go to an infinite height, or, well, whatever. So what's the most important part of that tube? What's the most important dimension? Its length or its radius? Radius, very good. And this is essentially water with some sugar and some taurine and some guarana and some magic ingredients. Okay. You guys know what that is? Also known as Monster. Okay. What if we had mercury or a non-wetting fluid instead? Then it would make a depression in it. We're not going to deal with that. We're going to deal with a liquid that has an adhesive tension. Okay. Who wants to take a good question? Mr. Liu? Does the type of fluid matter?
Yes.
Of course. What's really important is that adhesion tension. Okay. You scored one goal. Now let's see if you can score another. Is this a function of temperature? Is it a function of pressure? Probably.
Just a function.
Okay, very good. You get a hug. That's a good way of putting it. It's a weak function of pressure. We usually don't consider capillary pressure to be a function of pressure. We consider it to be a function of temperature, saturation, and the properties of the medium. Okay? Very good. Everybody's done pretty well tonight. Too bad we're not recording on the big screen, but that's okay. So this is an artist's conception of how to represent capillary pressure. So if we have big tubes, I did tell them to recalibrate this today. You can see they didn't. I guess these are full of blood. And it's literally 1 centimeter away. Okay. Let's see if I can draw a curve. Oh man, that had to happen. And remember, we were talking before, and I didn't draw it very well, sorry. So again, I didn't draw that very well. But that would be your largest tube, right? And that was what Mr. Ravi Kumar was saying. And this is your smallest tube. And unfortunately, I've drawn this incorrectly as well. I'm not a very good artist. But it should go straight up to infinity. Okay? So the smallest tube will control the irreducible, okay, or the smallest tubes will control that, and the largest will control this. What controls a shape? Well, I'm saying the shape of it would be the distribution of tubes. The distribution of tubes. So we have the largest tube controls the lowest height, the smallest tube controls the highest height, and the shape is controlled by the distribution of tubes. Okay? Well, that was easy. Now let's do this. So the way they've done it is all of these are the same diameter. Damn it. I promise I'll try to calibrate this tomorrow. And then like that. Okay. That's not exactly physically consistent because, you know, this connects with here, right? I can't change the color, but that's that case. So that has a very high irreducible saturation, whereas the other one has a very low irreducible saturation. Does this all sort of make sense now? Okay. Everybody happy? Now what am I going to do? Cam? That's CAM, not CAN. You're from Pittsburgh? What's the best way to get to Pittsburgh? Sorry? From here. You got to drive.
Well, I came down from Cincinnati.
That's in Pittsburgh?
Pittsburgh and Cincinnati.
Okay. Don't leave out any steps.
Straight flat.
Where does Cincinnati? No, where does it go?
Oh, like after?
Sorry?
I'm confused on what you're asking.
I need to know how you got here. Do you want me to put a map up?
Don't give steps.
This is one of those moments where I know God hates me. Okay, so you came from here. And how did you drive? What you went? You said this is Columbus, right? So you went here and then to here, and then to here. Eh? Louisville, Kentucky. Yeah, here. Okay. Well, how come you didn't go to Atlanta and go up that way? Sorry? Are you sure? Okay. But you came from here and you came over and down and went this way and over to here like this, but you could have just as easily have gone this way up through here up until there. Correct? If I told you that you had to go home this way, but you had to come back this way, what would that be? That would be path dependent, right? And so the word hysteresis means path dependent, okay? So when we drain the system, and it looks sort of like an hourglass, the drainage system looks like this. But when we refill the system, it starts at the bottom and goes up. So it's a completely different path. And what happens is during drainage, when we're reducing the wetting phase saturation, the path is this way. But when we're increasing the wetting phase saturation, the path is that way. Does everybody understand? There's a path dependency. We're having a big talk tonight about the realities of the situation. We have path dependency in our process, right? And then we promptly ignore it. How would you factor path dependency into an equation? That'd be pretty tough. You'd have to derive one equation for drainage and one for imbibition. And then you'd have to know which one's which. When we derive anything, what do we assume? Drainage. Why? It's the easiest. The wetting phase is decreasing. Also, imbibition will tend to trap non-wetting fluids. Mr. Bake, can I ask you a practical question that the math ladies might not understand? Math ladies, do you want to get rich? Really rich? You got to start your own oil company. And it has to be in West Texas. Unfortunately, right now is not a good time to buy. But maybe later, but not right now. And Mr. Baker is going to be your technical consultant. And what's he going to tell you to do? He's going to tell you to inject water. To do what? To use this process, the water will be drawn into the rock, just like it was into that tube, and it will displace oil out. Is that an effective means of recovering oil, class? Of course. Usually we don't think about it in this context. We think about displacing oil by pushing it out. But if you take a core that is saturated with oil and put it into a jar full of water, what's going to happen if the core is water wet? Everybody? The oil is going to bubble out of it. Okay? Now, in conventional systems, that's an easy way to recover more oil. How much more? A lot. It's a very efficient process. But we don't usually have the luxury of taking cores filled with oil and putting them in jars, do we? What's the name of the formation underneath us? We talked about this the other day. Sorry? Austin Chalk. Do you know where there's some Austin Chalk around here? No, where the closest place to you physically right now. The Austin Chalk is 3 miles down, right? Well, probably, maybe 2.5 or 2. I can tell you where there's some Austin Chalk with less than 50 meters. This building. The facing on this building is Austin Chalk. It's exposed, weathered Austin Chalk. That's why it's yellow. Okay. But the Austin Chalk is famous for having these huge fracture systems, right? So when they first started drilling the Austin Chalk in 1978 and 79, they drilled vertical wells. And occasionally, they would directly intersect a large fracture. And they would produce 1,000 barrels a day. And then maybe by the end of the week, it would be 100. And by the end of the next week, it would be 30. And then it would produce 30 barrels a day forever. Okay. But sometimes you would drill and maybe you would only get 100 barrels a day. And then the next week, you'd get 10. And then the weeks after that, you'd get 7. But forever. Well, that's a pretty good deal, except the well costs more than that. Right? So whenever they turned sideways, we got even more. We intersected more fractures and we were able to produce a lot more oil. But when they were still doing vertical wells, the companies had to figure out how to make money with these vertical wells that weren't producing very much. So what they did is they injected about a swimming pool's worth of water into the well and let it sit there for several weeks. And then they would produce it. And they would flush almost pure oil out of the system because the water went in and the oil came out. Okay. Not particularly effective long term, but it does work, and it's the same process. Okay. Now these are some definitions, and you don't have to take them for anything other than that, but this is a demonstration. If we had a sand pack, this is a height above the free water. The free water is here. As you can see, this is 100% water. And then there's a region called the funicular region, and the funicular region is where there's a rapid change in saturation with very little change in height. Okay? So there's a rapid change in saturation with very little change in height. So this obviously is a function of the size of the pore, the size and the distribution of the pores. Small pores, poorly sorted, this curve is going to be much higher. Okay? It'll take a lot more pressure to remove the same amount of fluid. And then the pendular region is where the only thing you have left is a little bit of fluid around these points of contact. And in fact, you'll never reduce it below that because it's physically impossible to have a high enough pressure to remove these pendular rings. Okay? And I'm going to jump ahead and skip this. You can read about that. Now, these are some physical curves. Unfortunately, they're mercury air. So these capillary pressure curves were determined by injecting mercury into the core. Injecting mercury. Those little cores that I gave you, ladies, you know the little cores? You put it into a device and it fills with mercury at zero pressure, at room pressure. And then you gradually increase it. So mercury is pushed into the rock. Do you think that represents oil and gas? Mercury's a liquid metal. Oil and gas are wet, right? They're fluids. I guess even though it's a liquid metal, it's still a fluid. But it's physically different than that. So how do you relate mercury with oil and gas? Or let's say oil and water. Anybody? Sorry? It's non-wetting, but I mean, not only that, it's not even physically the same kind of material. What's the molecular weight of mercury, or sorry, what's the specific gravity of mercury? And I'm sorry, I don't remember grams per cc. It's 848 pounds per cubic foot, which is 13.6 grams per cc or something like that. What is water? 1. So you've got a material that is very, very different than anything else you would inject in there. And as you mentioned, mercury doesn't wet anything except one thing, mercury. It also wets gold. Don't ever get your gold in contact with mercury. It will create an amalgam and it will just break off your finger. So it ruins it. How do you get mercury out of gold? Anybody got any ideas? Sorry? No, I meant, sorry, that's another question. I meant that if you got mercury on your gold, how would you get it out? You're taught that you should put it in an oven. But where does the mercury vapor go? Uh-oh, in you. So that's probably not a good idea. Okay, so this is mercury capillary pressure, and it's inverse saturation scale because it's so-called air saturation. But it's not really air, right? It's a vacuum. There's no air in it, but we just call it air saturation. And so what we're looking at is a curve defined by Tamir, and what you can see is that there's an intercept over here, and you could read off these values of the intercept. Now, if you're paying close attention, this is not 0. This is 0.01 because this is a logarithmic scale. But assuming it's flat, it won't matter. We're picking up the constant value here. Okay. Now, this comes from Jordan and Campbell, and I thought it was from Neesham, but maybe I'm wrong. And then you can tell that what's happening is the highest permeability sample is here, the lowest permeability sample is here, and basically it's a correlation of permeabilities for this. So could you correlate permeability for these samples? Could you take permeability and correlate it with that intercept pressure? Yeah. When was this first done? Does anybody remember? was done in the 60s by Kent Thomas and Donald Katz. What is Katz most famous for? Z-factor chart and other things. A whole bunch of hydrocarbon phase behavior correlations. So what they were trying to do is actually not exactly define a correlation of permeability and displacement pressure, but they were trying to prove that if the displacement pressure is high enough, it's essentially a reservoir seal. That was what they were trying to do. Now the Excel files that I include, this is Neesham's work, and Neesham shows the effect of different clays. Clays are materials that precipitate inside the pores. You can have discrete particle kaolinite, which is a certain kind of chemical compound, and you can have pore lining chlorite, which is another kind of chemical compound. It's like little hairs, and then you can have pore bridging illite, which is like really long hairs, and you can see that it completely corrupts the pore path. And these are photomicrographs at the time. I know it's really hard to see, but you can see the fibers coming out here, and you can see the particles sort of here. What they did is they also made a correlation plot of permeability versus porosity, and the discrete particle case, it's bad, but it's not too bad. And then the pore lining case, it's pretty, it has a big effect, but it still maintains this correlation basically of a straight line with porosity and or with the log of permeability and porosity. And then pore bridging illite just messes everything up. There's no correlation at all. I threw this line in just for your own benefit. Okay. So if we go back to the notes and I bring up the Excel files, there was some data in Archie. And this shows Archie's correlation of displacement pressure on the y-axis, permeability on the y-axis, displacement pressure on the x-axis. And you can see there's a couple of outlying points here, but that's okay. Generally speaking, there's a trend. Okay. And then if we come to the next one, which is the same data or the same work that we just saw a moment ago by Neesham. Let's see, I think I got the whole thing there. Yep. Okay, so the discrete particle is here. That's up here. The pore lining is here. That's here. And then the pore bridging is down here. So actually there's pretty good correlation. So if you were asking yourselves, can I correlate permeability with displacement pressure across a bunch of different types of rock, you can see that it does work. Again, this is just an exercise for discussion. Okay. So the next slide is a compendium of a whole bunch of cases from Neesham, and then the next slide is a discussion of Leverett. Leverett claimed in his paper, let's see, it was 1942, yeah, that he could create a universal capillary pressure curve, a universal capillary pressure curve. Mr. Beg, Mr. Ravi Kumar, you're chemical engineers. All he really did was define a dimensionless capillary pressure. What does that mean to everybody else in this room? He multiplied stuff by capillary pressure until the dimensions canceled. Okay? So he essentially defined this function, which is 1 over the interfacial tension multiplied by cosine theta, the angle, and then the square root of permeability divided by porosity multiplied by capillary pressure. And if you work the units out, it's dimensionless. Is it right? If this were correct, what would have happened to all the curves on that plot? They would have all been on top of each other, except he wasn't thinking that it's not just dimensionless capillary pressure, but it also has to be dimensionless saturation. Okay. So this is sort of a half-baked correlation. Now, knowing what I just showed you a moment ago, what would you define as the characteristic pressure in this dimensionless capillary pressure, what would you define it as? You'd use the displacement pressure, correct? The displacement pressure. The lowest pressure that represents the system. Why? Because it's convenient? Yep. No problem. All right.
So you essentially anchor all the curves at one point.
To the displacement pressure. But you also have to anchor all the curves to the irreducible saturation. And that means we're going to have to define another dimensionless variable. Remember, dimensionless variables are the variable divided by their characteristic. And in this case, the characteristic pressure we choose is displacement pressure. The characteristic saturation is irreducible saturation. But there's a trick, because irreducible saturation doesn't represent the movable pore volume. 1 minus the irreducible saturation represents a movable pore volume. So that's where that comes from. Okay. But again, this is now some 75 years ago when he defined this. And again, the goal of this was to create a universal capillary pressure curve. It didn't work. The units worked, but the concept didn't. Remember I told you also about Forkheimer's equation? How can you fix this? Eric? We need a relationship that has a dimensionless saturation function as well. Correct? But each of these curves has exactly the same shape. One? No. Mr. Desai? We're going to have an equation that has displacement pressure, irreducible saturation, and some kind of a term that represents the character of the curvature, right? If we were designing something to do this, this is what we would set out and do. Now, it gets a little complicated, but we're going to do that in a minute. So then these are some other curves. These are from Leverett, where he was using his dimensionless capillary pressure curve, and he shows you that it doesn't work very well, but that's okay. Now, first thing we'll do is talk about the derivation of the rise of a fluid in a capillary, just like we did. So in our case, the external is air. In our case, the internal is water or monster. And what we have is we have a rise in this tube, and the pressure across here and here. The differential is defined as the capillary pressure. It's a balance of forces. The force up has to be equal to the force down. No problem. We understand that. The force up is the adhesion tension. The force down is the mass or the weight of the fluid as it's being pulled down. The force up is very easy to define. How does that force act, people? It acts on the circumference of the tube, which is 2 pi r. And what is acting on that? Anybody? It's the adhesion tension. What is the definition of adhesion tension? What are the units? It's dynes per centimeter. So dynes per centimeter multiplied by centimeters is dynes. Dynes is a force. So it's force up, force down, equal. Now we have to go through some discussion about how to define what the adhesion tension is, and that's what this discussion is. So the adhesion tension is a resultant force. We have a solid material. We have fluid. It could be water. We have another fluid. It could be oil, or it could be gas. And then we have an angle of incidence, and that angle of incidence is measured through the wetting phase. Okay? In theory, what should the wetting phase angle be for water, class? It should be 0. A strongly water-wet system will pull it all the way out, right? What's the cosine of 0? 1. Okay. So if we assume a strongly water-wet system, then that term goes away, and we're just left with the interfacial tension. Okay. And again, our upward force is defined by the interfacial tension multiplied by cosine theta multiplied by 2 pi r. Our force acting up, our force acting down very quickly is just going to be the density multiplied by the height, multiplied by the cross-sectional area, multiplied by G over G sub C because we use the US unit system. And then that gives us, when we finally work it all out, 2 times the adhesion tension divided by radius, or 2 times the interfacial tension multiplied by cosine theta divided by r, which is exactly where we started before. So in simple terms, it's very easy and rigorous to derive the capillary pressure equation for a single tube. Okay, everybody's okay with that? Now things get crazy because now we're going to use a bundle of tubes. Okay, this was where I talked about how to use the concept of in the old days, they would say that what you would do is you'd have the capillary pressure at one condition and you could relate it to the capillary pressure at another condition. And that's what this is. For simplistic terms, you could say that the capillary pressure related to an oil-water system can be related to a gas-water or gas-oil system by using these relationships. It's just a rescaling. And what you're doing is you're assuming that R over 2 is your constant, and then you're setting the equations equal. And by that, you get a relationship that defines the capillary pressure at one condition and the capillary pressure at another. I'm going to skip the derivation of the Leverett function. I'll let you guys come back to that. And I'm also going to skip this. You can come back to that. So what I'm going to do now is talk about type curve matching. And this will be very fast. I don't want to keep you too long. But what we do is we take the Necorn-Tappan-Evans result. I'm sorry for the quality of this, but you can read through it. This is our permeability relationship. And then we take our permeability relationship and we input our capillary pressure relationship from Brooks and Corey. Remember, it has to be dimensionless, so we define our dimensionless pressure as capillary pressure divided by displacement pressure. We need a dimensionless saturation, which I'm going to say is 1 minus SW star. SW star is defined above as SW minus SWI over 1 minus SWI, so it's normalized saturation. So SW star is 1 minus SWD. That'll become obvious later on why we need SWD. We go on ahead and make the substitution for the units, and you can do that by substituting all the definitions there. So this is the final form for the units. Now what we do is we take the Brooks-Corey capillary pressure equation and we insert it into this expression, and when we do, we end up with the displacement pressure squared out front. We have an integral from 0 to 1 of the normalized saturation raised to 2 divided by lambda. We perform the integration, and when we do, that integral is 1 over displacement pressure squared, and then that lambda term divided by lambda over 2. And again, lambda, or reciprocal lambda, is the coefficient in the capillary pressure equation. Okay, that's all fine and good. What does it really mean? Well, now we have an equation for permeability based on that. That's the definition that we'll work from. There was also some work done by a student who's actually now in Houston, but he was an a graduate student with me, and he had worked on this, and he claimed that we could define beta as 1 over porosity and n as 1 over the quantity 1 minus SWI. It was sort of an empirical hand wave, but I went on ahead and put that in. We still have an alpha parameter out front, which is sort of a fudge factor, if you want to call it that. Now what we're going to do, pardon me, I went too fast, is we'll take the Brooks-Corey capillary pressure equation and we'll write it in terms of saturation, not normalized saturation. And we somehow need to make this dimensionless. Again, we're going to define the left-hand side by the displacement pressure, and what do we have to do on the right-hand side? Well, on the right-hand side, what we want is a dimensionless formulation, not the normalized formulation. So I went on ahead and I said that the dimensionless capillary pressure was, the dimensionless saturation was going to be 1 minus SW divided by 1 minus SWI. It's a little bit different than what we had been working with. So when we do that, we actually have a reversed scale, and I've drawn a picture of it over here. So we would have these type curves, which would be the dimensionless capillary pressure here and the dimensionless saturation. That's these lines. And then I've superimposed on top of it a data set. I know this is completely meaningless, but just bear with me. So the displacement pressure is the capillary pressure at the match point divided by the dimensionless capillary pressure at the match point. The irreducible saturation is 1 minus the 1 minus saturation at the match point, and then the SWD at the match point. Again, we're plotting 1 minus saturation on this axis, not saturation. You can see that here. Okay, so that's fine, but let's look at it in PowerPoint. Ready? Okay, so there's the type curve. Sorry, I think this thing's going to auto scale on me. I don't want it to. Okay, there we go. So here's the type curve, and again, it's dimensionless saturation. Why did it convert to that? Ah, I switched to PowerPoint. Okay. PowerPoint, because of the product, it likes the pen. Okay, so there's dimensionless saturation or dimensionless pressure. There's dimensionless saturation, and again, it's 1 minus SW base, so it's going the opposite direction. And then we have our individual curves, and this thing's so far out of calibration, there's no way you'll understand. But suffice it to say, for those of you who can see, this is a poor geometry factor of 1/4. This is a poor geometry factor of 10, so you have a whole family of curves here. Now, someone could say, oh, geez, let's use the derivative of this or something crazy like that. Yeah, we could. But let's just stay with reality check right now. So here's a data set. This is an actual data set from the literature. So we have capillary pressure plotted on the y-axis. We have 1 minus saturation plotted on the x-axis. Okay. Everybody close your eyes for 1 second. Eric, close your eyes. Okay. Somebody tell me how to match this data set on top of this type curve. What do I do? Where does it fit? Does it fit there? No. Does it fit here? No. Where does it fit? Cam? Does it fit there? How about right? How about right there? So now, if I use our friend here, what's your favorite color? Red. Red's good. So there's my fit of the data. Not bad, huh? That's how you would work a type curve. That was really fast. But you'll have the video so you can go back and take a look. You're going to be tested on this? No. You're going to have to rederive it? I can't remember. Anybody want to look it up on the syllabus and tell me? Did I make you rederive it? I don't think so. How come I got to do all the work in this relationship? Feel free to say something funny. Derive capillary pressure for a single tube. We did that. Derive the permeability relation for a bundle of tubes. Yep, that's in the notes. Derive the field unit form. Yep, we did that. Derive the Brooks-Corey-Perm relationship for absolute permeability. Yep, that was there. And then tomorrow we'll derive the relationship for relative permeability. I don't see the type curve thing in here, so you can breathe easy. Of course, maybe it'd make a good exam problem. I don't know. Maybe you guys would kill me. Yes, Eric.
So how does a computer do a problem like that?
Okay, so if we wanted to do it the way you're discussing it, that's a great segue into this. We would just that was a bad idea. That works. Okay. You just put that equation into solver. Okay. But that's a no-no. Mr. Ravi Kumar, we're going to let you redeem yourself. Why is solver bad and type curve good?
For this problem or general?
Okay. Let's say generally.
Because I'm constraining your, because it might give you,
You know what the limits are.
it might give you random values.
You cannot you cannot exceed certain parts of the equation. Now, having said that, obviously you can set up constraints inside of solver. But if we solve this problem with solver and we solve this problem with type curve, we better get exactly the same answer. Well, it's within reason, we should get the same answer. Okay. Is there a way of solving those parameters directly without using a type curve? That's Jeopardy for those of you who don't know. You have 1 minute to tell me.
Take the log and then
Okay, you take the log of both sides of that equation, and what do you get? Correct. But you have to know K N O W. You have to know what in that equation in order to do what you're describing. Do you have to know PD? Nope. Do you have to know lambda? Nope. Because PD is the intercept and lambda is the slope. So what's SWI? You got trouble. Okay. Because the whole thing will shift depending on the SWI value.
but you can split that equation up. You can split the PD.
You can?
Log PD plus log of that terms.
Really?
I mean, once you take the log,
Really?
um,
I think you're inventing some new math here. You're saying that the log of x minus y can be split?
no, I'm saying, oh, okay, yeah, I see.
I'm old,
No,
I'm slow,
PD and-
but I guarantee you, I know you can't split this.
I was talking about PD and SW, but I didn't get your point.
Okay. Everybody feel good about this? How many of you have read the Benson paper? Nobody's read anything yet. Gabe, what's the Benson paper? When you were an undergrad, you said you had Dr. Valco? What has Dr. Valco invented? Has he ever told you? Not really. Yeah. He's got a few things under his belt. He invented regularization of B-splines to do deconvolution. We shared a student on that. He's invented a number of different well solutions, derived a multi-well productivity index. He did the work on the Grace algorithm. He implemented that. I don't know if Dr. Valco were here that he'd take credit for any of those, but he should. You know. But does he have some white whale, some Moby Dick in his life that he solved but he can't prove, or he's not solved but he can prove? I don't know how to put it. Does anybody? I'm just picking him at random. Does every person have a Moby Dick somewhere in their career? Something they couldn't solve? Yeah. You should. Okay. Remember we talked a little bit about Papet, and he derived permeability as a function of fractals, which was absolutely brilliant. Unfortunately, it's completely impractical. So what Benson did was he used Gibbs free energy. Remember that, Mr. Begg, Mr. Ravi Kumar? Some chemical engineering stuff. And he derived capillary pressure from that. Okay. Unfortunately, he ended up with a lot of unknowns. He has a nice equation that he comes out with, but it came out from making some assumptions about some unknowns. He has some things that I guess I'd almost say in theory you can't calculate. But that was his Moby Dick. It's a nice paper. And I remember talking to him one time about it. I think I was a young faculty member. I may have still been a graduate student. And I asked him, what motivated him to do that. And he goes, but it answers all the questions. And I was like, oh, yes. Yeah. Everybody has a white whale. And this was Benson's white whale. You kill it or it kills you. His approach to capillary pressure was from the most fundamental approach. And his equation actually has a power law component. But the power law is really easy. Why, Mr. Ravi Kumar? Because you can easily linearize it. But what if instead of PD being multiplied by that, PD was plus that? That would make life really miserable, wouldn't it? And that's the form that Benson ended up with. He ended up with a form where PD wasn't a multiplier, but it was a scale. It was an additive scale. How many other functions for capillary pressure? There's plenty. That you could make your own if you want. Why do we use the power law? Again, because it's easy. It's conceptual. You can make a straight line out of it. But what do you get when you integrate a power law equation, class? A power law formulation. So that worked out really well. What do you get when you integrate Benson's relation, and it's not on here? You get a headache, a really big one. Okay. So you think it's okay to take mathematical conveniences? Yeah. Okay, as we continue, I want you to remember that there's a lot of cheating that went on in engineering. I started to say petroleum engineering, but in all engineering. Mr. Bate, Mr. Ravi Kumar, what is the one thing you can never cheat? You can even cheat those to some degree, but what can you never cheat? You can even cheat that to some degree. Mass balance. You cheat the mass balance, the whole thing will fall apart. I don't know when, and I don't know where. It's like a singularity in the universe, but you are going to pay the price if you cheat material balance or mass balance. And you guys haven't had this course with me, but whenever I talk about some of the work that Vetkovich did in the late 1970s, early 1980s, he cheated the material balance equation to end up with a closed form equation. You can't do that. It doesn't. The math may work, but, you're going to end up going to Pennsylvania by drilling a hole in the earth, ricocheting off of China and coming back up, and that ain't going to work. You're going to go through Georgia to go home next time?
No, my
No.
ex-girlfriend lives there.
Sorry?
Said no, my ex-girlfriend lives there.
In Pennsylvania or in Georgia?
No, Atlanta. That's why I didn't go. Not a thing.
You got an answer for everything. I like that.